Hey guys, today we're going to be going into detail about our second assignment for 209, where we implement a tiny shell. In the beginning, we're going to demonstrate that the code runs without any errors. In the beginning of the code here, we initialize a couple of variables that we will be using for eval later on. We initialize a buffer and parse the command line using parseLine, which splits the command line into an array of arguments. We then check if the command is meant to run in the background or not by inspecting the end of the command line arguments and checking whether it's an ampersand or not. Moving on, we handle the built-in commands with built-in CMD, which is a function we'll get into later. We check if the command is built-in or not. An example of built-in commands is quit, bg, or fg. We do this because we might get into more complicated scenarios where we might have to use piping. In that case, we count the amount of pipes that we have, and this is very important because the number of pipes determines the number of commands that we're going to execute and how many child processes we need to fork.
Now we're moving on to one of the most important parts of the method. So setting up and managing pipes and processes. So for each pipe, we need two file descriptors, hence the array fd pipes, its size pipe count multiplied by 2. We then create these pipes in a for loop. Each successful pipe creation call populates two file descriptors, one for reading and one for writing. With the pipe set up, we loop once for each command to be executed. So in each iteration, we prepare an array, which is called partition argv, which will hold the arguments for the current command. The partition pipeline function is called to fill the array and to handle any input or output redirection by setting input fd and output fd. For forking a child process, we block certain signals to avoid race conditions. Our child process is created with the fork method. In the child process, we first ensure it runs in its own process group with set pgid. This is going to be crucial for job control, which eventually will allow the shell to send signals to groups or groups of processes.
All right, for each command, if it's not the first, we might need to set up its standard input to come from the previous pipe. If it's not the last, its output might need to go to the next pipe. We handle redirection from files with the dup2 method, which duplicates the file descriptors for input or output redirection onto standard input or output respectively. After we set up the file descriptors, the child closes all pipe file descriptors because it doesn't need them anymore. We then unblock signals and execute the command with execve. If execve fails, we print an error and exit the child process. Back in the parent process, after all the children are forked, we close the pipe file descriptors as they're no longer needed. If the command is not meant to run in the background, the parent waits for each child process in the foreground to finish, which ensures proper sequential execution of these commands. Finally, that covers all of eval, and we'll move on to the next method. Over here, we have partition pipeline. We initialize some variables and we look for the piping operator. If we find it, we go and put the command right before it into the list. Otherwise, we look for any of the redirection operators for the reading or the writing. And if we find those, we deal with them. We set up the input and output files. Otherwise, we just move on.
The built-in CMD function that we talked about earlier is implemented here. We check if it has quit, jobs, bg, or fg. If it has quit, we loop over the jobs and we exit. If it has jobs, we use the given method list jobs to print out the jobs that we have. Otherwise, if it's bg or fg, we use the function do bgfg, which we're going to talk about right now.
First, we check if the ID is null. If it is, this means that the user did not provide the necessary argument. And depending on whether the command is fg or bg, we'll print the appropriate error message, noting that this command requires a PID or the job ID as an argument. If an ID is provided, we first check if it starts with the ampersand. If an ID is provided, we first check if it starts with a %, which indicates it's a job ID. When we use the atoi function to convert this ID into an integer, ignoring the percentage character and call the getJobID to retrieve the corresponding job. If no job is found, we print an error message stating that no such job exists. and again, exit the function. In cases where the ID does not start with the percentage, we assume it's a process ID. We again convert the ID to an integer and use the getJobID to find a corresponding job. If no job was found, we print an error message yet again. Once we have a valid job, we attempt to send a sigchld signal to the process group of the job. This is done using the kill function with the job's PID and the sigchld signal. Finally, we check that the command used fg or bg. If it's fg, we set the job state to fg, which is in the foreground, and call the waitfg. And we pass in the job's PID. This function will make the shell wait until the specified foreground job completes. If the command is bg, we simply print the job's details, including its job ID, PID, and command line. And then we set its state to background, allowing it to continue execution.
All right, now for waitfg. Initially, a signal set named mask is prepared and the sigchld signal is added to it. The signal is crucial because it's sent to the shell when a child process such as a foreground job changes states like terminating. The shell then blocks sigchld signals temporarily to prevent handling them before it's ready. The current signal mask is saved in prevmask for later use. The core of this function is for us to wait as long as the PID we're waiting for is still associated with a foreground job. We check this using fg_PID of jobs. This ensures the shell remains working on this until it's complete. Within the loop, sigsuspend is called with prevmask, which temporarily unblocks sigchld and puts the shell to sleep. After sigsuspend finishes and it's woken up, the loop checks again if the job is still running. If the job has finished or is no longer in the foreground, the loop exits. Finally, the original signal mask is restored, reblocking sigchld if it was blocked before, ensuring the shell's signal handling returns to its previous state.
The sigchld handler function here manages changes in the child process states, specifically to do with terminations or stops. We start by saving the current error value to preserve the shell's error state, and then this loop right here uses waitPID to check for any child processes that have exited or stopped without blocking, if no children have changed the state. Then for each child process reported by waitPID, signals are temporarily blocked to safely update the job list. If a child was stopped, the job state is updated to ST or stopped, and the message is printed. If it was terminated by a signal, a message is printed and the job is removed from the job list completely. And then after handling the job, signals are unblocked and the loop continues to check for more child processes state changes. Finally, the original error value is restored, and the function ensures that the shell's job list accurately reflects the current state of background processes, handling terminations and stops due to signals efficiently.
When Control-C is pressed, it signals an interrupt with sigint. The sigint handler gets invoked. It retrieves the PID of the currently running foreground job using the fg_PID. If there's an active foreground job, the handler sends a sigint signal to the entire process group of that job, which will terminate it. Similarly, the sigtstp handler is called when you click Control or when you press Control-Z, which sends a signal indicating a pause, which interrupts the handler. It checks for an active foreground job. If it exists, the handler sends the signal to the process group of that job, suspending it. Both handlers ensure that the signal actions are directed at foreground jobs, allowing background jobs to continue unaffected.
We also implemented a few of our own tests. For the first one here, we check if foreground jobs can resume after stopping and having multiple background commands run. And for reference, the second test we implemented checks that multiple input and output redirections can happen together. And for reference,
All right, for the next test, number 20, we check that the signals are stopped when it comes to the background jobs. And now for the reference. Okay. Now for the next test, number 21, we test that piping works and that it works with redirection. This one, we can't show the reference shell because it doesn't support piping, but as you can see, it works. It calls cow an input and then sorts it as needed. Finally, for test 22, we test multiple pipes with redirection as well. As you can see, this one also works.
Now we're going to talk about some challenges that we ran into while working on the assignment. The biggest challenge we ran into was debugging. Debugging in C is generally challenging due to the absence of a built-in tracing feature. This makes it difficult to pinpoint errors and understand their origins, especially in complex systems or with concurrency issues. The way we dealt with this was with alternative debugging strategies such as print statements and basic test cases.
Now, on our second problem was adding piping functionality at the end of our code. This forced us to rework our entire system's logic, and this was quite difficult because we were given a lot of liberty while making or implementing piping. So this was kind of difficult since we had to incorporate it with our existing code. What we did to help this was going over the PCRS, reviewing the piping man pages, and we adopted an incremental integrational approach where we just broke down each task into smaller ones, and we did it step by step.
Overall, when it came to overcoming challenges as a group, the way we took care of this is by organizing our thoughts on an organizational chart. We drew examples, we broke them down step by step. For example, when it came to piping, when we had the pipe of 2 commands, we figured that out, and then we made it so that it worked for multiple pipes. And we did this by drawing, by sitting and talking about it, and it ended up working. When it came to debugging, we all worked together on it. Each person gave ideas for test cases and came up with good solutions. And overall, we split all the 6 methods accordingly, and everyone did their fair share. That's how we ended up finishing this assignment.
First, I'm going to demonstrate that the code runs without any errors. Okay.
Now we'll check if ID is null. If it is, this means the user did not provide the necessary argument. Depending on whether the command was FG or PG. I'm so sorry.
Bro, what?
First, we check. I'm so sorry.